let's find the electric field due to a uniform charged sphere. And I'm going to do this two ways. That's two ways, right? So first I'm going to use Gauss's law to do this, and then I'm going to do it in Python with a bunch of tiny points. It's going to be awesome. Okay, so here's my sphere. It's a radius r, charge q, and I want to use Gauss's law. So Gauss's law says the following. Gauss's law says the flux, the electric flux E dot n hat dA over some closed surface is equal to Qn, the total charge inside of that surface, divided by epsilon naught. How can we use that? Let me draw a better picture of this, because what we need to do is I want to find the electric field inside the sphere first. Okay, so here's my sphere, and it's uniformly charged. And suppose that I pick another sphere inside of there of radius lowercase r. Why would I do that? Because if I make some assumptions about the electric field, and this is key, you have to make some assumptions about the shape of the electric field. If I assume that the electric field is spherically symmetric, because why wouldn't it be, then when I draw that sphere inside of my total sphere, that Gaussian surface as a sphere, then the electric field is going to be perpendicular to the area in all points, and constant magnitude over that whole thing. So this is going to make this integral doable. Okay, so in this integral we need the electric field n hat as a unit vector pointing away from that surface, and dA is the area element. And this is a complete closed surface. That's why there's a circle right there. So here's my E, and n hat is going to be in the same direction. So E dot n hat is just going to be E, right? Because E and n hat are always going to be in the same direction because of the sphere that I picked. And E is constant on the surface of that sphere. So in fact, I can change this integral to this. I can say the integral of E dot n hat dA is E times the integral dA, right? I can pull the E out since it's constant. Now I just have to integrate over the surface of that sphere of the area element dA. Well, that's not too bad, right? It's just the surface area of a sphere. So I get E times the surface area of a sphere is 4 pi r squared. 4 pi r squared. And that's going to be equal to Qn over epsilon naught. Now, I do have a problem. What is the charge inside of that sphere? I need to find that. I don't want the total charge Q. I want the charge inside of there. Well, if we go back to here, and if I assume it's uniform charge density, then the ratio of charge to volume here and the ratio of charge to volume of here have to be the same. So I can say Qn over the volume of this sphere. The volume of the sphere is 4/3 pi r cubed. Has to be equal to this charge Q divided by its volume, 4/3 pi r cubed. And you know, here I said r, and here I said r, right? So those are different those are different. But you knew that, right? Well, look at that. 4/3 cancels, pi cancels, and I get Q over r cubed equals Qn over r cubed. And so Qn is going to be equal to Q r cubed over r cubed. So let's put that in up here, switching to a new piece of paper, just so I have plenty of space. So I have this. I'll write it the same way. E times 4 pi r squared, right? That's the surface area. Qn is this, is equal to Qn q r cubed over r cubed, and then I have the epsilon naught down there. And now let's just solve for the magnitude of E. So I'm going to divide both sides by 4 pi r squared, and I get E equals Q r cubed over r cubed epsilon naught 4 pi r squared. Well, look at that. Cancel, cancel. So this is going to be equal to, I'll write it as 1 over 4 pi epsilon naught Q r over r cubed. And that's E. But notice before I check this value, let's notice something very important. This is the scalar magnitude of the electric field. It does not give me the direction of the electric field. And that's because I've already chosen the direction. I already picked the direction here by assuming the direction of the electric field. I assumed the shape of the field in order to get this magnitude. Okay, so it's not the same as just saying, oh, I'm going to get the electric field from scratch. I had to make some assumptions. Okay, let's check some things. Units. Well, what are the units for this? I know, let's go back over here. E equals 1 over 4 pi epsilon naught Q over R squared R hat. That's the electric field due to a point charge. So the units for this and the units for that have to match. So I have 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught. I don't need the 4 pi, but I do need the epsilon naught. I have Q. I have R squared on the bottom, and here I have R over R cubed, so it does have the same units. Okay, R equals 0. What happens as R goes to 0? Well, if I go back over here at the center of this sphere, then I should have, according to Gauss's law, no charge in the center, and it should be a 0 electric field. But also, if I go back over here, all these charges are going to make electric fields symmetrically pointing towards the center, and they should cancel. So I should get 0. And if you put in R equals 0, you do get 0. So that checks. Check, check. What about as R goes to infinity? Well, this says the electric field blows up to infinity, and that's bad. Okay, that's bad. But it's fine, too, because we did this assuming the electric field inside the sphere. So now we actually need to do outside the sphere. This one's not too bad. Let's draw another Gaussian surface. Do the same thing. Here's my sphere. And there's my charge, uniformly distributed. And I'm going to pick a Gaussian surface that looks like this. It has a radius lowercase r. And again, I'm going to assume the electric field is uniformly spherically pointing outwards, so that the integral of E dot n hat dA is going to be equal to E times the integral of dA. Same thing, right? It's the same thing. So I get E times 4 pi r squared. Now what about Qn? In this case, Qn, it doesn't matter how big my sphere gets, the total charge inside is still just Q. So it's just Q over epsilon naught. And now if I solve for E, I get 1 over 4 pi epsilon naught Q over R squared. And that's the same as the electric field due to a point charge. So that's good, right? Outside of a spherically symmetrical thing, you get that. Now let's just go over here. E equals 1 over 4 pi epsilon naught QR over R cubed. What about at E? This is E outside the sphere. This is inside. But what about on the surface? Well, E at the value of R, let's put in R up here. I get 1 over 4 pi epsilon naught Q over R squared. Let's put in it over here. 1 over 4 pi epsilon naught QR over R cubed. So the R's cancel. I get the same value at the surface. So these two solutions match and meet up and agree. So that's kind of a big deal. Okay. Now let's do this again without using Gauss's law. Well, remember that if I have a point charge right here, Q, just a tiny little point charge, and I have an observation location, RO, right here, that's the vector RO, and let's call this the vector RQ, I can find the vector R, and then the electric field is 1 over 4 pi epsilon naught Q over R squared R hat, where R is RO minus RQ. So this is the vector from the charge to the observation location, and then the R hat as a unit vector in that direction. So I get an electric field, and that's important. Now what if I have two charges, say a plus there and a plus there, and I want to find the electric field right here? Well, I have the electric field due to that one, the electric field due to that one, and then E is just, let's call this E1, let's call this E2, E is E1 plus E2. So it's just the sum of the individual electric fields. I can take any number of charges that I want, and I can just add up all the electric fields. So how can I represent a uniform charge sphere with a bunch of point charges? Well, imagine that I have this. Here's my sphere. And I put a bunch of point charges in here. Let's say there's 100 or 1,000. It doesn't really matter. But those are all my charges. And I want to find the electric field right here. Well, I just do this 100 different times, right? I find my observation location. I take the difference between this point charge and that point charge, the vector, and I find the vector electric field. And then I do it for this one, and then that one, and 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 I add it all up. Now, I don't want to do 100 calculations, so I'm going to make Python do it. So let's do this in Python. Now, we do need, in Python, we're going to add these up as vector values, but we do need some numbers. So let's just pick R is 0.01 meters. That's the radius of the sphere. Q equals, I don't know. I'm trying to think here. 3 times 10 to the negative 6 coulombs. I don't know. I do need some values. And I do need this 1 over 4 pi epsilon naught is 9 times 10 to the 9th. And I'm just going to call that K. Let's do this in Python. Now, we do need to do some tricks here about random numbers, but I'll just do that all over here. Python time. Okay, hello, Python. So I already saved. I put K in there. Let's put my other values in there. Is that big enough? I don't think that's big enough. That's better. Q equals, what did I just say? 3 times 10 to the negative 6. And then R equals 0.01. Okay. Now I need to make a sphere with a bunch of charges. So let's say N equals 100. I want to make 100 charges. And N equals 0. So I like to count this way, right? So I'm going to increase my value of lowercase n until I get to N. And that way I can change things up. And there's a lot of ways to count, and that's just the way I like to count. You count your way too. Okay, so while N is less than N, I want to make a random variable vector. Okay, I'm going to make a random vector in 3 dimensions. I'm going to call this RT. So RT is going to be R, the radius of the circle, times the vector. Now we can make, I'm going to make random points in here. I want these to be uniformly distributed. One way to do that is to make them random. So I'm going to make a random value between -1 and 1. To do that, I can say 2 times random minus 1. So random gives you a number between 0 and 1. And if I multiply it by 2, it's between 0 and 2. I subtract 1, I get -1 to 1. Now I need to do that in the x, y, and z. 2 times random minus 1. 2 times random minus 1. And then I multiply the whole thing by r. So now it's between -0.01 and 0.1 in the x, y, and z direction. Let's go ahead and draw a sphere at that location. So sphere, I'm not even going to give it a name. Position equals RT. And then the radius, let's make this radius r over 50. I don't know. And now I need to increase my value of n. N equals n plus 1, or the loop will go on forever. And that's just awkward. Okay, so here we go. Run it. It worked. Okay, you never know when that's going to work. Now, that's not a sphere. That's actually a cube, right? And that's only 100 points. Let's do 500 points just so we can see it a little bit better. 500. And you see that is a cube, right? That's not a sphere. So what I want to do is to generate these random values and then cut up the ones that aren't in a sphere. I can do that. So over here, what I'm going to do is generate that random vector. And now I'm going to say if the magnitude of that vector is less than or equal to the radius of the circle, then I'm going to make a sphere. And then I'm going to add 1 to the thing. So otherwise, I'm just going to throw that thing away and just make a new one. So if I do that, let's see what happens. I'm still only going to count up to 500 if it meets the criteria of being in the sphere. Boom. That's a sphere. And I can zoom into it too. See? It's a sphere. That's a sphere. Okay, and that's only 500 points. We can do more than that. Okay, now I need to kind of like reference all these values. And I don't even want to draw them because it's just going to slow down things. What if I want to make 10,000 or 20,000 points? So I want to add my Q's into a list. So I'm going to call this QS. I guess I should call it RQS. because it's a position. RQS is going to be equal to an empty list. I also need dq, the charge of each point, which depends on how many points I have. It's going to be q divided by n, the total number of points. Okay. Now down here, I'm going to leave the sphere on for now just so we can see. I'm going to draw the sphere. I'm also going to add that vector to my list. So I have a list of all the vector locations of all my charges. RQS equals RQS plus square bracket RT. So that's going to make this giant list. I'm not going to print it, but I will print the length of it. Let's just so we can see. Let's just print, just to show you that it is real. RQS, I'll print out the first one, and then we'll print out the length. Print the length of RQS. Okay, let's see if that works. That'll give us validation that it is in fact doing the right thing. Okay, so it is 500 units long, and there's one of the random variables. It doesn't really matter. That's just what it is. Okay, so we're good now. Let's get rid of the sphere, because I don't really care about that. Now what I want to do is to go through the list and calculate the total electric field. Okay, so to do that, I'm going to start off, I'm going to go through each point. I'm going to calculate the vector from that point to the observation location, which I don't know yet. So let's say ROBS is going to be equal to 2 times, let's say, vector, 2 times R00. So it's outside the sphere. Okay, and that's what I picked. And then I need to pick, I need to add the electric field due to each point charge at that location to the total. But I don't have a total. So let's make a total. E total equals vector 0, 0, 0. So I need something to add it to. Okay. Now I need to go through the list for RQ in RQS. So this will go through the list RQS and call each element RQ, and then I can do whatever I want with it. So the first thing is to calculate R. R equals ROBS minus RQ. And now I can calculate the electric field. I'm going to call it DE. It's K times DQ times norm, which is the unit vector R, divided by the mag of R squared. Now I'm going to add that to the total. ET equals ET plus DE. And that's it. Let's print that out. E equals ET. And let's also print the theoretical value, just so we can check, right? Print E, this T stands for theoretical. It's going to be K times Q divided by R squared. Yeah, KQ, yeah. No, it should be 2R squared. That's the distance. Okay, let's see if this works. It might not work. You never know. It might not work. Okay, I think it worked. So here's my X component of the electric field. Notice I got a vector value. These are smaller, but not 0, right? They're 100 times smaller. 10 to the 7th, 10 to the 5th, 10 to the 5th. But this is very close to that value. So it seems to be working, and that's only with 500 points. If I run it again, I'm going to get something different because it's based on random numbers. Okay. Now what I want to do is to take my observation location and move it and make a plot of the electric field magnitude as a function of position. To do that, I'm actually going to make this a function. This whole calculating electric field is going to be a function. So def E, and I want to give it RO. I want to pass it. I'm going to pass it a vector observation location. It's going to use the existing list of charges, and it's going to return the electric field, the total. So all this stuff needs to be in the loop, in the function. So ET is my temporary vector. That still works. That still works, except here I have RO. I called it RO. Everything's fine, and then I just need to return ET. And let's just, no, yes. And so let's over here print E, change that to a function, ROBS. So it should give the same thing, right? I just turned it into a function instead. And I might have made a mistake. Sometimes mistakes happen, and that's fine. Okay, it works. We're good. Okay, Now what we can do is to move our observation location and plot the electric field at all these points. Let's make a graph. G1 equals graph. Title equals E due to sphere, which is bad, but that's fine. X title equals R in meters. Fine. Y title equals E in volts per meter. Width equals 400. Height equals 200. And then I need a curve to plot. F1 equals G curve. Color equals color dot blue. Label equals Monte Carlo. Because this is my Monte Carlo calculation. When you're using random numbers to generate stuff like that, it'll be a Monte Carlo calculation. And I'm labeling it because I'm going to make another graph. Okay. Now I need to pick a step size. How far am I going to move my thing each time? So let's say dr equals r over 20. I'm just picking that. We can change it. Doesn't really matter. And I'm going to start at the center. So let's put this at 0. There's my function. I don't need this stuff. So now what I'm going to do is I want to move ROBS. So while ROBS.x, the x value, while that's less than 2 times r, right? So I'm going to get up to that same position. Then what do I need to do? I need to plot my value of my electric field. So f1.plot, the x coordinate is going to be ROBS.x. My y value is going to be the magnitude of E ROBS, right? So I can't plot E because it's a vector, but I need to take the magnitude. Now I need to move my value of ROBS. So ROBS equals ROBS plus vector dr0, 0. I think that should work. Let's just see. I should save it though, shouldn't I? Okay. So remember, inside the sphere, which is at right here, the edge of the sphere, it's linear. Now, that does not look linear because what's happening is that if I get too close to a single point charge, I can get a very large electric field. And that's only 500 points. So let's repeat this with 1,000 points. That's easy to change. 1,000. Looks a little bit better. It's still not perfectly linear, but this outside looks very nice because we're not super close to any of the charges. And we'll check if that is indeed the same thing. Let's do 10,000. It's going to take a little bit longer. That looks pretty good. I'm pretty happy with that. You can increase the value more. I'm going to give you the code down below. Just be careful. I'm going to give you the code. Okay, now let's make another curve. F2 equals G curve. Color equals color dot red. Label equals Gauss. So that's Gauss's law version. So what I'm going to do is to calculate the Gauss law value of it and then and plot that. Okay, so to do that, down here in my list, as I'm moving R, I need to calculate the theoretical version, but that depends on where I'm at. So if if ROBS.x is less than R, then I'm going to calculate that as E Gauss is I'm looking at my equation that I derived. I'm going to type that in. E Gauss is K times Q times R, which is ROBS.x, divided by R cubed. And I'm going to plot that. F2.plot ROBS.x EG. Okay. Otherwise, I can just put else. Then EG is K times Q times divided by ROBS.x squared. And I'm going to plot that. F2.plot ROBS.x EG. And I'm calculating the scalar values of that. And that should work. Let's see what happens if it runs. I'm going to be super happy. There you go. Okay. Boom. So you see outside the sphere, the two match up really well. And even inside the sphere, that's a very good approximation. Every time you run it, it's going to be a little bit different. I got a spike there. I got too close to something, but it's not so bad. Let's run it again. Oh, a bigger spike. That's even worse. Okay, well that's a good one right there. That's a good one. But again, running it multiple times gives you different things. So that's Gauss's law. Two ways, just like I said. Link to the code down below. The end. I'll talk to you later.